Well, what we're looking at here is an hp5314a universal counter. And it's a very nice little unit. It's in excellent shape and it does a lot for the shop. With it you can measure frequencies up to 100 megahertz. You can measure periods. Periods are important when you are trying to measure low frequencies in particular. You wouldn't get much resolution on this measuring, say, 10 hertz. In fact, 10 hertz would show up as 0.01 hertz. But when you measure period, you're measuring the number of microseconds you can count during the single cycle. So you can measure 1,000,000 microseconds in 1 second. So you could measure 100,000 of them in 1/10 of 1 second. And that would give you a resolution that's a heck of a lot greater. So you measure period with this, and that gives you some capabilities, especially in the low frequency areas that you wouldn't otherwise have. And another thing this does is it will measure the ratio of two frequencies. So if frequency A is 10 times higher than frequency B, it will display 10 on the display and tell you that that ratio exists. So if you have a lower frequency that you know the frequency of, but maybe you don't know the higher one, then it'll tell you the ratio, and you multiply that ratio times your lower known frequency, and you know then what you have. And another thing it will do is to measure time intervals between events. It will count the number of microseconds that elapsed between a start and a stop. So you could the start would be triggered by the leading edge of the signal coming in on A, and the stop would be on the falling edge of channel B. All of these are described in a very nice manual that I have that goes along with this counter. It's a fairly thick manual, but it will take you through. In this case, this is the period measurement setup. Here's the time interval and so on. It takes you through each step, tells you exactly how to set the switches. And along with this, we also have schematic diagrams, layouts, calibrations, and so on. So it's a full service manual. And what we want to do is we want to try and utilize this meter, take it through a couple of steps. Right at the moment, I'm only utilizing channel A at the moment. We'll disconnect channel B just so it's clear that that's what we're doing. And what we see is that we are displaying 0.1 kilohertz on the display. That's 100 hertz. So I have, coming in on channel A from this top signal generator, I have 100 hertz. That's the resolution I see for 100, 0.100. That's not a lot of resolution, and that's what I was talking about for the period. Now, if I measure the period, I'm measuring right now 9,984 microseconds in that period. So maybe I'd want to try and adjust my frequency to make it exactly 10,000, or as close as I can get to it. And that would put me at 100 hertz, exactly. That's pretty dang close right there. So I should be able to lift this, go back to the setting, and I see 100 hertz. 10,000, 100 hertz. So that's the use of the period measurement. Now let's go ahead and take a look at the higher frequency end of this. Like I said, this is a 100 megahertz counter. Right now we're on the 1 hertz setting, and that's going to limit me to I think 10 megahertz. Right now I'm reading 10 kilohertz, 100 kilohertz, 1 megahertz, 1,000 kilohertz, actually 1,013 kilohertz. And if I take it much more than that, we're going to go over range. And we actually, our amplitude changed a little bit. But we are over range, so what I'm going to do is kick ourselves up again. We're back in range now, and we are seeing we're at 8,088 kilohertz. So that's 8.088 megahertz. Alright, right now we are reading about 25 megahertz. 25,000 kilohertz is 25 megahertz. We are on the 100 megahertz range right now so that we can see this. If I go back down one, we lose everything because we've gone over range. And period measurements are limited in range of 100 milliseconds to 400 nanoseconds, which means we can measure frequencies of 10 hertz to about 2.5 megahertz. After that, it doesn't work anymore. So, which that explains why we were not getting anything when I was trying to measure 25 megahertz. However, we seem to be having no trouble actually measuring periods. That's 1 megahertz. There's 2. I should be able to drop this down to 1 or 2 and see the same thing. Alright. That's roughly 1 megahertz right there. I guess that would have to be up there. And we can change the range and get a little more definition there. So that's a megahertz. And if we go to 2, we should be half of that. That should be 2. And if we go to 4, we should be about 2.5. Now, we're not supposed to be able to measure 4, but this thing seems to be responding. 2.5 would be right there. And just for fun, let's see what the frequency is now. 2.5 is 4003 megahertz, or 4003 kilohertz. It's 4 megahertz. So we were right on. So that's a period measurement. Okay, at this moment what I've got is I have both generators hooked up. I've got the A and the B generator. The B generator right now is set for roughly 10 hertz, and the A generator is set for about 100,000 hertz. And we're coming into the unit here, and I've got the switches set now so that we're reading the ratio of A to B, A over B. So A right now is 100,000 hertz, B is 10 hertz, and we're getting a ratio right now of about 10,000. 10,083, but 10,000. So A is 10,000 times what B is. B is 10. That means A must be 100,000. And we already know that A is about 100,000. So the relative ratio of A to B is what we're measuring here. Now we can change, let's take A down a decade. So we'll go from 100,000 to 10,000. And we see that we drop now so that A is 1,000 times B. B is 10 hertz. A must be 10,000 hertz. A must be 1,000 hertz. A must be 100 hertz. A must be equivalent. So you can see we're reading ratio. We'll take a look at intervals in a minute. Okay, at this point I have the unit set up to totalize. That means that for every pulse it sees coming in on A channel right now, I will count up a pulse. We are right now at the moment reading the frequency. We're reading 10 hertz. I'm going to put it in the totalize position. And we're going to start counting. For every pulse that goes in, we're counting at a 10 hertz rate. And it will count until it completely fills up the counter, or until I stop the counting. And we'll know how many pulses went through in a given time. If we were reading slow running pulses and we weren't sure how many pulses we were going to get out of a train, we could use this capability to count the number of pulses and give us that information. I can stop the count, hold it, pushing the hold button in. Resume, and I just turned off the generator. We've stopped the count. Turn down the generator and we're counting again. So that's the totalize. Okay. So what we're doing now is that we have a calibrator with a crystal time base in it, and we're going to check the frequency readout for the various settings of this calibrator. Right now we are set for 20 microseconds, 20 microsecond period signal, which is 50,000 hertz. And you can see we have 50. I'm going to take it down to a 50 microsecond period. We get 20,000 hertz. This is a 100 microsecond period. We get 10,000 hertz. 200 microsecond period, we got 5,000. 500 microsecond period, we got 2,000. 1 millisecond period, and we have 1,000 hertz. 2 millisecond period, we have 500 hertz. 5 millisecond period, we got 200 hertz. 10 millisecond period, we have 100 hertz. 1 millisecond period, and we have 50 hertz, or excuse me, this is a 20 millisecond period. We have 50 hertz. 50 millisecond period, we have 20 hertz. So we were able to resolve to within the capability of this counter exactly all of those frequencies. Now, on the low scale, which we're on right now, 20 hertz, we ought to be able to go to the period, and it'd be interesting to see what kind of a period reading we get. So let's go ahead and do period. Alright. We're getting 50,000 microseconds. 50,000 microseconds would be 50 milliseconds. We are on the 50 millisecond division. All I did was just adjust the gain a little bit for the input. It stabilized it. Now if I go to 20 milliseconds, there we are, 20,000. It's 20 milliseconds, 20,000 microseconds. 10,000 microseconds. 5,000 microseconds. 2,000 microseconds. 1,000 microseconds. 500 microseconds. 200. See, at this point you'd be better off reading frequency because you'd have better resolution. And just to prove that point, let's go back. And there we go, we got 10,000 hertz. Hertz or 100 microseconds. Take your pick. Okay, so there you have it. Well, here I have the shoot-off between the hp5314, the Gold Star FC7012, and the Philips PM6673. And as you can see, all three of these are actually tracking very closely to within the first 6 or so digits. They don't track necessarily at the same moment because their intervals are just slightly different, but they are tracking the same frequency significantly close, which is as it should be if the oscillators are all adjusted properly in these units, and I believe they are. So we're getting good readings out of all of them. Right now I'm running at 25.5 megahertz roughly, or 24.5. It's the extent of my my signal generator in this case. And I'm going to start dropping the frequency, and we'll see it start to track. We're at 23.5, 23.3, 23.1, 23. Let's go to 23 even. So let's make it 20 even. Let's do that. Have fun with that. 20.5, 4, 2, 1, 0, 0, 2. My Philips has flaked out a little. There we go. 1999. 20.01, 03. 0.16 on all of them. We'll go ahead and take her down more. Take her down to 10. There we are, 10.008. 3, 2, 1. We break into 9.995. And they're all three breaking at the same point. So that's the whole point. These things are working well. The HP is the brightest of the three units. It is the cleanest looking, and the HP also measures frequency, period. It has two inputs and will measure the ratio of one against the other. It has a hold, so you can hold the display if you care to. Right now I've frozen the display. We can release it back to normal and let it vary if we want. We have adjustable front end gain. Actually, we've got enough signal strength coming in right now that gain's not even necessary, but I can put the attenuator on, and there we've lost it. Now if I turn the gain up, we get it back. Down, and back. Same thing for channel B. Has a nice case, has a stand that works. Nice unit. Happy bidding. I nearly forgot. We also have a complete service manual on this universal counter. Covers operating and service information both. General information, installation, operation, performance tests, adjustments, replaceable parts, manual changes, services. And along with it, besides all of the information on the unit, I've also provided the schematics on 11x17 for ease of use. Board layouts. Functional diagram. So there you have it. Nice manual, nice unit. You should be all set. Thank you.